Okay, we've been talking about the ear structures. Now we want to actually turn our attention to the microscopic level. How do we hear? Well, this is a section right here of the cochlea. Now the cochlea has actually got three chambers. Now I can bottom line this for you very simply by saying your sense of hearing is dependent upon moving fluid pressing on a membrane between these chambers. All right, if you remember, the stirrup is attached to the oval window on the vestibule. Now that oval window is filled with a fluid, and as the stirrup moves back and forth, it causes the fluid, and that fluid is called perilymph, in this chamber right here. It causes this fluid to move at the same frequency as all the bones are vibrating. As those waves pass by, they press down on this membrane, this vestibular membrane. They push down on that, and that creates a movement in this section, the cochlear duct. And the fluid is a little different. There it's called endolymph. As that fluid moves now at the same frequency, it presses against this techular membrane, which presses little tiny hairs in these cells. This is your hearing sense right here. The organ of Corti is your actual organ of hearing. Every time this techular membrane is pushed up and down and bends these hair cells, that sets up an action potential which goes through the cochlear portion of the vestibulocochlear nerve, carries the sound waves to your head. Now in a two-dimensional picture like this, it's kind of hard to visualize this whole process. That's why I picked the next slide, which kind of stretches this whole thing out a little bit. Consider this. Because what if the cochlea, instead of being coiled up, were straightened out? Well, I think that simplifies understanding how this works. That's why I pulled this slide up here, mostly for this picture on the bottom, this down here. If you were to unwind the cochlea to where it's all stretched out like this, kind of like it is in alligators and other reptiles, then here's your stirrup pressing against the oval window, and as it's pushing here, it's pressing down, it's pressing on against this fluid, the perilymph, as it goes down. As it presses against the perilymph is going to press down against this membrane, the basilar membrane. And this is where it presses down on that basilar membrane, this is where it triggers those hair cells. So all across here, from the oval window all the way to the end, you've got a whole bunch of little hair cells, all part of the organ of Corti. Now, each region of the cochlea is sensitive to different sounds. Let's say, for example, your ringtone on your phone was geared towards, let's say a longer wavelength, a longer frequency. It's going to stimulate hair cells all along here, but when it gets out to this region right here where they are most sensitive, it's going to stimulate them even greater. Now, if you've ever seen or have a ringtone on your cell phones, for example, that adults cannot hear, I hope you've heard of those, because I didn't hear about these until I actually saw one work. Here's how they work. People older, like your teachers, me for example, years of loud music, I have worn away the hair cells at this portion. Well, if this is the portion that is most sensitive to high frequency, and it is, this part here close to the oval window is responsible for the higher frequencies. If this portion right here again is responsible for the high pitches, and my hair cells right here are worn out, I'm not going to hear high pitches. I'll hear these low tones out here that require less energy, You have to kind of imagine that we've got like keys on a piano. One end, high pitches. Other end of the 88 key piano, low pitches. Now, a real quick explanation here about physics and waves. The distance from one crest to the other is one wavelength. So if I were to go wavelength right here, that's one wavelength. And the height of the wave, from the high to the low, this is the amplitude. One thing you need to remember about sounds is that louder sounds have higher amplitude. So if you were looking at this right here, these waves like this would seem much louder than these over here. Okay, let's turn our attention now to the balance. Balance or equilibrium. The receptor cells for balance, again, are mechanoreceptors, just like hearing. They're going to be in the vestibule, which includes the utricle and the saccule, and the semicircular canals. Now, in these, let's take a closer look here. This whole structure right through here, and again, it's hard to diagram this in 2 dimensions. 3-dimensional models we'll use in lab tomorrow will make this a lot easier. But this vestibule is going to be divided into a large portion, large bulge, like this one over here, which is the utricle. And this is going to be responsible for detecting the horizontal movements of your head because of the way the special receptor cells called macula are arranged. The saccule, those special receptor cells, it's still called macula, are arranged vertically. So the saccule is going to be responsible for picking up your head tip or tilt. The semicircular canals still are mechanoreceptors, and 3 semicircular canals. You have one that goes up and around here, and again, in 2 dimensions, it's awful hard to get across here. But they run 90 degrees to each other. And I always use the example of a gymnast or a diver. You know, if a gymnast is doing a front or a back flip, it's going to pick up that rotation as they flip forward or backwards. And it's going to stimulate little tiny receptor cells called the crista ampullaris as that fluid moves around. Whereas if a gymnast were doing a cartwheel, it would stimulate the crista in another semicircular canal. And if the gymnasts were doing a twist of some sort, they would be stimulating the crista in 2 different semicircular canals in different directions. So the gymnast can actually pick up their speed and direction. Now let's look at how the macula actually work. Now the macula are the special receptor cells that are found in the vestibule, detecting static balance. Here's our basic setup. In this picture right here, we've got them set up here to where you have the otolithic membrane, which is really more like a jelly. And in this, you've got little tiny specks of a bone-like material we call the otoliths. The hair cells in here, the hair cells with their hair tufts sitting up here, are sitting up here with their cells, the hair, embedded in this membrane, and these otoliths kind of pressing on them. So when your head is in the upright position, those little calcium carbonate crystals, the otoliths, press on it, and when they press those hair tufts down, they send a nerve impulse to the brain to tell you that your head's upright. Now, if you tip your head forward, like this, the force of gravity is going to pull that jelly-like material to one side. It's going to pull that otolithic membrane to one side, and as it does, those otoliths are going to press against those hair tufts and send a new message to your brain that your brain interprets as, okay, I'm tipping down. And this still connects to the vestibular portion of cranial nerve number 8. So this explains our head positioning, or our static balance. To the dynamic equilibrium, or movement. The structure here is called the crista ampullaris. These are located at the base of each semicircular canal. You'll have one of these little tiny crista ampullaris here, these structures shown right here, which has a structure called a cupula surrounding little tiny hair cells. Now, what happens is this. In the semicircular canals, you've got a clear fluid called endolymph. Now, remember Newton's law of motion, law of inertia. Objects at rest tend to remain at rest. Objects in motion tend to stay in motion until acted upon by an outside force. So this endolymph is following Newton's law of inertia. It's kind of sitting still. But as soon as you move your body, shove it, the apparent flow of endolymph is in the opposite direction. Really, it's not flowing. It's sitting in one place, but the body's moving. But the endolymph is going to cause the cupula to bend. When this bends, it sends an action potential here through these hair cells. That sends the message to the vestibular portion of the vestibulocochlear nerve to your brain that says, hey, I'm flipping forward, flipping backwards, spinning around. That's where all those messages come from. So it's all based around this cupula, which is being pressed by the endolymph. So what happens when you're spinning around in circles and all of a sudden you stop? You get dizzy because, let's take Newton's law of motion now, law of inertia, the endolymph is pushing the cupula around. All of a sudden, there's no movement. The cupula stands back up, but the endolymph is still moving. You feel dizzy.